So today we're going to start talking about the atomic mass. We're going to start talking about why the atomic mass is a decimal point when the mass number is not. So the mass number we know is like protons plus neutrons, and the protons have a mass of 1 AMU, and the neutrons have a mass of 1 AMU. So when you add all those ones and all those ones, you get a whole number, right? So that's why you don't get a decimal point for the mass number, because it's just a bunch of ones, protons, and a bunch of ones, neutrons, which have a mass of 1 AMU. But the atomic mass is an average of the atoms. It's an average of the isotopes. So when you have a sample of carbon that occurs naturally, in that sample is, remember, carbon 12, carbon 13, carbon 11, all these different isotopes are in that one sample. It's not simply carbon 12. In the sample that you scoop up of carbon naturally would be a bunch of different isotopes. So because of that, you have to average them out to get the atomic mass. And when you average anything, you get a decimal point because you're dividing by a set number, right? So we're going to take a look today at a graph. And this graph is going to be something called a bell curve, which is a statistical anomaly, which is super important. It's a big deal. It's one of my favorite things, bell curve, because everything falls into a bell curve. Everything you can possibly think of. Everything falls into a bell curve. Anything you can think of. Okay? So we're going to draw a bell curve. And then we're going to fit a few things into it. So let's draw the bell curve, and let's put the point right here, a little bit to the left, to the right. I'm going to draw my peak, kind of like this, just because that way, I know it should be like right, why isn't it right over a line? But later, it's going to be useful for the drawing of boron, which is what we're drawing ultimately. But for right now, we're just drawing a generic bell curve, which is going to go like this. It's supposed to be symmetrical. And this is the peak. And the peak is at the highest number of whatever, of items, or people or whatever. But in this case, it's at the largest number of atoms. So the peak is the largest number of atoms, or the largest number of people, or the largest number of whatever. But we'll talk about that in a second. The largest number of atoms for us, for our graph. But I'm going to use a different, to explain a bell curve, I'm going to use the average height of men in the United States. And then I'm going to use the average height of women in the United States. So we're going to use right now the average height of men in the United States, which is 5'9". Here it is, 5'9". So the average height of men in the United States is 5'9". If one is over 5'9", one is taller than the average height. If one is under 5'9", one is shorter than the average height. The greatest number of men are at 5'9". See, that would be the largest number of men. Okay. If I go to 5'10", there are fewer men. If I go to 5'11", there are even fewer. 6 feet, even fewer. 6'1", greatly fewer. And then it starts to drop off rapidly. When I get to 6'2", 6'3", 6'4", there are very few. 6'5", 6'6", almost none, right? Okay. Statistically, of course you know people who are 6'6", but how many? Not many, right? But there are, sure. Okay. Going the opposite direction, same thing. 5'8", yeah, definitely there are some. Yeah. Okay. 5'7", sure. 5'5", sure. Yeah. Don't know that many, but sure. 5'3", there are, but not very many. Just like 6'3", right? Not that many, but sure, you might know one, two, maybe three. Okay, and on down to 4'9". Yep, they exist, but not that many, like 6'7". You just don't know that many. You might even know one in your whole life. Maybe you will, maybe you won't. Okay? So this is called a bell curve, where the highest number is here, and as you drop off, statistically, so drops off the number. Women, 5'4". 5'4". 5'6". 5'8". Sure. 5'8". 5'10". 6 feet. Yep. 6'2". Yeah. Okay. Right. Okay. Same thing. 5'4". 5'2". Yeah. 5'6". Right. Okay. Down 4'11". Yep. They exist, but there aren't very many. Right. 4'10". Not so many. Yep. Okay. On down. Now, bell curves can be used for anything. Absolutely anything. You can come up with any phenomenon in nature. You can come up with any phenomenon in life. You can come up with people who love trains. Okay. People who think trains are okay. Yep. Most people think trains are okay. There are those who are completely obsessed with trains, and when you walk in their house, they have trains everywhere, and all they think about all day long is trains. They're like trains. They can't have a relationship because all they can talk about is trains. There's very few of them, but they're there, and there they are, way down here, right? They're way down here. How many are there? You might not even know one in your life, but they exist, don't they? And then there are people who are terrified of trains and hate trains and never want to go near a train. And if they even see a picture of a train, they like curl up in a ball because they have train anxiety. There are very few of them. You might not know one, but they exist, right? Okay, and as you get closer to, trains are okay. As you get closer and closer and closer, the numbers rise, yes? So I'm about here. I really like trains a lot. There aren't a lot of us. But, I happen to like trains a lot, so I'm probably around here because a lot of people really like trains, but not as many as feel completely neutral about trains, right? So, and there's a lot of people who don't like trains, but you know what? Not as many people as feel completely neutral about trains. You get my picture? This is a bell curve. There's a bell curve for everything. In nature, there are bell curves for weight of deer in the winter. There are bell curves for offspring of woodchucks. There are bell curves for the breeding season of alligators, starting with whatever it is, January, and ending with whatever it is, October. How many times an alligator has sex? Right? How many times an alligator? Well, right around there, there's a peak right here. There's the peak in June, because that's the peak season for alligators to have sex. Everything has a bell curve. So we're going to look at a bell curve today, and we're going to look at it in terms of 10, 11, 12, 13, 9, 8, and 7 in terms of the mass of isotopes in boron. Now, the atomic mass of boron there can also be like slanted bell curves that look like this, right? So the skewed bell curves, they're called skewed bell curves. All right, so bell curves are a really big deal, and when you get to statistics, when you take statistics, you learn all about bell curves. All right, and atomic mass is equal to 10.81, and then the mass number is equal to 11. So you can see the peak number of the largest number of atoms is right about 10.81, right? Or 11, somewhere right around 10.81 or 11. So this would be the sample of, I scoop up boron, a scoop of boron. All my isotopes are included in here. Where is the largest number of atoms in here fall? They all fall right around in here. Why is that? Because my atomic mass, when I round them all off, is going to be 10.81, somewhere around 10.81 to 11, right? So the largest number of atoms will fall right in between here, between around 10.75 and 11. That's where the largest number of atoms will fall, right in here. Because if I look on the periodic table, boron, number 5, 10.81. So the largest number of atoms will fall right in there. Okay? Got it? The question is, how can we calculate the atomic mass from all these isotopes? If we have all these isotopes, right, these atoms that have different masses, how do we calculate that 10.81? Well, we have a process, and this is such an important process that it is tested on the AP test. It's called weighting. So what we're going to do is we're going to take this sample of calcium, which has 3 isotopes in it. We have 100% of the isotopes broken down into their percent representation. And we are going to use the practice of weighting as in putting weight on each isotope. Okay, so we're going to do this weighting thing where what we're going to do is if 99% of the sample is one isotope, we're going to give that 99% of the weight. All right, so this is how we're going to do it. I'm going to take my decimal point and I'm going to move it 2 places. And the reason is because it's a percent. All right, so I'm going to take 0.0413. Oh, nope, sorry. Nope. I'm going to take 0.413. I apologize. Okay, let's try that again. So we're going to take 0.413. That moves my decimal point 2 places, from 41.3% to 0.413. I'm going to multiply this times the mass number 39. So that is my percent and my mass number. I'm going to add this to 0.327 times 40 plus my last one, 0.260 times 41 equals. So now I'm going to do all of this on my calculator in one calculation. So I'm going to say, opening parentheses, 0.413 times 39, close parentheses, plus open parentheses. 0.327 times 40, close parentheses, plus open parentheses. Sorry, I meant to clear the whole thing. So what I'm doing is, I don't know if you can see that. Can you see that? How's that? Can you see that? So what I'm doing is I'm putting each calculation inside the parentheses. And so my last one is going to be 0.260 times 41, close parentheses. I'm putting each calculation into the parentheses and then I'm adding them together. All right? Now, when I get my answer is going to be 39.85. Now, how do I know that my figures should be 39.85? The reason I know this is because they asked me to find the atomic mass. And in Miss Paxton's class, our atomic masses go to 2 digits after the decimal point. So that's what we're doing, 2 digits after the decimal point. All right? And what are my units here? What are the units for the atomic mass? Yeah, AMU. Atomic mass units for atomic mass. Okay, AMU. So I'm going to zoom in again on my calculations, zooming in. So I took 0.413 times 39 and 0.327. So each one of these percentages weights, W-E-I-G-H-T-S, weights the mass number. Let's try the next one. So in the next one, we have, instead of the mass number, we have this percent abundant. Instead of the percent, we have a percent abundance. So it's the same as a percent, right? And then the next thing we have is, instead of a mass number, we have an AMU, which is fine. We can still work with that. It's the same thing. So we're going to move our decimal point, 0.0759 times 6.015. Now, when we're done finding our atomic mass, it says, calculate the atomic mass of the unknown element X, and then identify the unknown element, which is medically used to treat some mental disorders. Okay. Plus, now I'm going to move my decimal point 2 places, 0.9241 times my mass, 7.016, equals, use my calculator, so I'm going for 2 after the decimal. So I get 6.94 AMUs. So I need to determine what element that is. How am I going to do that? 6.94 is my atomic mass. How can I do that? Yep. So I'm going to go to my periodic table. Right? I'm going to go to my periodic table and I'm going to look up the 6.94. And what do I get? Rebecca, what do I get? Lithium it is. Excellent. Thank you, Rebecca. I get lithium. Now you'll notice that here, this was my percent abundance, which I moved my decimal point 2 places. And this was my mass. This mass came in AMUs. Okay, now, and this mass, so I still used the mass, yeah.
Why do you write in the answer, why do you write AM instead of AMU?
Oh, it's AMU.
Oh.